Hey everyone, it's Adam again, and we're going to continue on with our 7th lecture here about fitting models to data. So here are the objectives we're going to cover today. And the first thing we're going to talk about today is going to be simple linear regressions. So the goal of linear regressions, and this kind of goes back to when we were talking about correlations previously, is that when we do a linear regression, we basically are trying to find the best fit line through a graph of various data points based on the sample that we're looking at. And so with linear regression, we're fitting basically a simple model to the data, and that way we're trying to determine basically the most likely values of those parameters that help to define that model. And so basically what we're going to be looking for is both slopes and intercepts. And this is going to be basically the goal here is to take a sample set. We're going to find the linear regression that helps to fit the model best, and then we can apply that then to other patients. And hopefully this is going to be predictive, assuming that we have a good sample that we're pulling from and the linear regression we did was good. And so, for instance, if we go back to that insulin resistance data that we were talking about in the last lecture, we saw that there were two variabilities we're looking at, including both insulin sensitivity of the patients and that fraction of the fatty acids, the carbon chain length that they had there. And so looking at it, the researchers were trying to propose basically a simple model that they could apply then to other patients. They were saying that with insulin sensitivity, it's a linear function of that percent of those fatty acid chains that they had that was 20 to 22 carbons. And basically what they were postulating was that as the percentage of those fatty acids go up, so does insulin sensitivity. And so what they were able to find was that they could make a model off of this based on basically the insulin sensitivity you would predict that a patient has would equal the intercept plus the slope times that percentage of the fatty acids that the patients had. So basically insulin sensitivity would be on the y-axis, the percent of fatty acids there would be on the x-axis, and then we'd see the interslope would be the variable b, and then slope is going to be m. So I'm sure everyone is familiar with the equation for a line, y equals mx plus b. Here you can see how it can be just kind of rearranged briefly. Now, of course, models do not account for random variation, and you may find that if you develop this model or this line and you try to apply it to a different set of patients, if they were not sufficiently similar enough to the original set of patients, or the data was incorrectly gathered, things like that, you may find that it would not be very accurate. So that's why one of our big goals is try to determine what are good, accurate models and apply that to other patients, and they retain that accuracy when doing that, and that can be very useful for applying it to lots of different patients in that case. But we'll say that, in these cases, the investigators are using that standard assumption that, random variability that they're finding from those predictions of the model, they're going to follow a Gaussian distribution, or should be normally distributed there. And so basically the goal here is to find those values for the intercept and the slope. They're going to most likely be correct, and they will quantify any precision that we can have there with confidence intervals. So basically we're going to say that, this line may not be perfect, but we'll have the 95% confidence intervals so that were you to apply that back to another random sample out of the population that you were interested in, you could at least get it within that range there. And so we'll look at these models as graphical representations, which we'll see more in just a little bit. And so basically we're going to find that with the help of linear regression, we're going to find the line that best predicts y from x, right? So in this case, it best predicts insulin sensitivity from the percentage of those fatty acids. And so we're going to look at this, and we're going to consider vertical distances of the points from the line and see how that variability around that line can interfere with our predictions. So if you're looking at the data we were talking about before, so again, looking on the y-axis, we have insulin sensitivity. Here on the x-axis, we have the percentage of those 20 to 22 carbon length fatty acids. And you can see based on the data, even though it's not a perfectly straight line, so that R value was definitely was positive, but it wasn't 1. I think it was like 0.77 or something like that. You can see this is the best fit line that goes through all those data points essentially. And notice that really none of these points actually fall on the line itself. And that's okay. And you're going to find that some of the variability can be accounted for with the 95% confidence interval that kind of can be shaded in around this line. So based off this data, with this kind of limited data set, we could then researchers could apply this back to say other groups of patients, assuming they were similar to the patients in this sample here, and say that, hey, we're 95% sure that if we were to get someone with say 20% these fatty acids, we could predict that with a 95% confidence interval that their insulin sensitivity would be somewhere between, say, 275 down to, let's say, right around 200, right? So they're 95% sure of that. Obviously, they can't say specifically, yes, it's going to be this number because they don't have the enough precision to do that. Again, here's a table that kind of is analyzing the data we saw in that previous graph that would be, spit out if you were to use some sort of like statistical program or something like that. So this one here is called GraphPad Prism. And other programs will be able to format those this information differently. But and again, we're not going to be focusing on every single data point here. But one of the things we can look at is see that based on that information, we can see what the slope is going to be. We can see where the actual intercepts are going to be at here when both y and x are going to equal 0, and then also their 95% confidence intervals are listed there. We're also going to talk about the goodness of fit test, and this is going to tell us how good our line is actually fitting to the data. And so we'll see that the R squared value is going to come up again. And again, the higher you typically want to get this number as close to 1 as possible, so that way the data is fitting to the line very, very well. Here we can see that that's not the case, but we're going to look at that in more detail just a little bit. So with linear regressions, we saw that on the data we were looking at that the slope was 37.21 plus or minus 9.269. So again, there's a little bit of variability there. And so we saw that if you were to increase the percentage of the fatty acids by just one integer, the average insulin sensitivity is expected to increase by 37.2 milligrams per meter square per minute, right? And so you would, again, based on this, you could possibly apply it to other patients and see that would be accurate or not. And so here we'll see the 95% confidence interval. The slope ranges anywhere between 16.7 up to 57.7, so pretty wide range there, but does not include 0. So that would actually give us pretty strong evidence that that observed relationship is just due to random chance alone. It's more likely to actually be not just a random chance that we would get this kind of slope with these confidence intervals. So again, non-zero being something we're looking for there for significance. Now the intercept here, the y-intercept when x is 0 is negative 486, and so this line gets defined by both the slope and the y-intercept. And so when the value here of the insulin sensitivity, what that value is when the C 20 to 22, that percentage there equals 0. For our example, we're going to find that because that value is negative, the y-intercept is not going to be really scientifically relevant. And so that negative result tells us that, when that linear model cannot be correct when extrapolated beyond that range of the data, right? So, if it gets to kind of impossible numbers, you're going to see that there's maybe only a range where that line is actually appropriate. And so that can be found when you're looking at values like this that are pretty extreme and kind of not physiologically possible. So again, the graphical results, it's going to show us the kind of best fit regression line defined by those values for the slope and the intercept that gets determined by that regression. And that shaded area shows us that 95% confidence bands of that regression line. You'll notice that only 6 of the 13 data points actually were included within the confidence bands, and that's going to be because the bands themselves are going to be more based on the actual regression line and not on the data points themselves. So again, it's okay that some of those data points are not going to be included in that 95% confidence interval. It doesn't necessarily tell you that the data is bad or by any means. It's just something you're going to find when you're looking at linear regressions like this. So one of the things we can see here on this graph is that, again, the shaded portion here is a 95% confidence interval. And so we come up with a best fit line, but that may not be the exact line that you would see if you plotted out the entire population. And that's why we can say that, hey, we're 95% sure that somewhere in the shaded area, the line exists, that it could be applied back to that population. So you could see there could be several different lines that could be possible here. And that's why we have such a range here. Now, obviously, if we were to say have a larger number of people we were looking at, say instead of 13, we're looking at 130, you'd probably see these confidence intervals actually start to shrink, and you have a much more narrow band here where you can determine where your actual line would be when applying that back to the population. So we mentioned that R squared value here is 0.5929. So basically what we can say is that 59% of all the variance in the insulin sensitivity can be accounted for by the model. That means that we still have 41% that are accounted for by other factors. So this could be due to things like biological variation, measurement errors, or if there is a nonlinear relationship between the two values here. Okay, we'll talk more about that a little bit later. But basically just know that when we see an R value like this, we can basically say that 59% of that variability in the Y value is going to be determined by the X value essentially. P-value is here, you're going to see this is going to be significant. It's less than 0.05. And so if we were to say what the null hypothesis of this this example would be, it would be that there's no linear relationship between insulin sensitivity and the percentage of the fatty acids. And again, the p-value is saying that if the null hypothesis were true and there were no relationship here, what is the likelihood that we would see a best fit line that would have basically a line that was as extreme or more extreme than this, that kind of deviated from a slope of 0, because again we looked at that previously and saw that an R value of 0 would be no relationship between the two variables. And so because this is a tiny p-value, it's very unlikely that this kind of association will be made just due to random chance alone. We can say that we can reject the null hypothesis and that there is a linear relationship between looking at the insulin sensitivity and the percentage of those fatty acids. So again, correlation and linear regressions tend to be related. So if we're looking at, say, a null hypothesis for a correlation, it's that there's no correlation between x and y. And then the null hypothesis for a linear regression is that the horizontal line is actually correct. So we would say that there, again, line of 0 means no correlation there between the two. Essentially, the two null hypotheses here are going to be equivalent, and so the p-values for correlation and the linear regression of this data are going to be actually identical in this case. So when we're looking at our assumptions for a linear regression, one, that the model is going to actually be correct. We're going to find that not all relationships are linear. Some of them tend to be linear for a portion of certain values and then tend to maybe skew off maybe towards being more exponential. It could be lots of different things, but again, we can see here that our assumption is going to be that this relationship is linear. The linear regression equation, though, defines a line that actually extends infinitely in both directions. So that's why we saw that when you got down to an x value of 0, the y was negative, and that would be physiologically impossible. And so you can see here that it's only going to lie within a certain range. And so we can't necessarily determine just from our data here what that range could actually be. But we're working with the assumption is made that the relationship between x and y is linear within a defined range, within the range of x values that we have, as we see in the example of the insulin sensitivity. So other assumptions we're going to make is that the scatter around the line is Gaussian, so it should be normally distributed. Variability is going to be the same everywhere. For the given x values, that variability should be roughly the same amongst all the data points. Data points need to be independent, and again, as what we saw with like unpaired t-tests and things like that, data has to be independent, or that's an assumption we're making at least, and that the x and y values are not going to be intertwined, meaning that the x is not being used to actually calculate what the y value is and things like that. They need to actually be separate measurements, and then the x values are known precisely would be the other assumption we're making here. So for comparison linear regression and correlation, we can see that basically correlation quantifies the degree to which two variables are going to be related. It doesn't really fit a line to it or best fit line, and this will tell us what the kind of the extent or at least the direction that one variable tends to change when the other one does. And here we're not really thinking so much about cause and effect. And in this case, it doesn't matter which variable is x or y. These are really kind of two interchangeable because you're really just looking for how much one changes with the other, and it should be consistent no matter which way you were actually to graph that. And again, no cause and effect is being associated with this. We're just looking for correlations. Regressions, on the other hand, is when we need to start thinking about cause and effect. And so again, we're looking to find a best line that predicts y from x. So again, this is not the same line that would happen if you were trying to predict x from y in these cases. So we are making that assumption, we're at least making our hypothesis that the lipid content x is affecting the insulin sensitivity y. Again, not the other way around. You wouldn't want to flip this and say that, okay, the insulin sensitivity is dictating what kind of lipid content. And so a lot of times you have to go back to what your kind of your hypotheses are about the actual biological association is here. But again, we're thinking more cause and effect rather than just looking for a correlation. So we're looking at our linear regressions. Obviously, they're linear, which means that it's describing a mathematical relationship between the model parameters and then the outcome. And we're going to see that you can have a simple linear regression, and then there's also multiple linear regressions. Simple just means that we're only looking at one set of variables, so only one x variable and one kind of outcome y variable. Whereas when we're looking at multiple linear regressions, you're going to find that you can look at two or more x variables. That's going to be one of the big differences there between simple and multiple. So once we have kind of a linear regression, one of the things you can actually do is determine a model. Okay, so what we'll find is when we're trying to take some data and try to fit a model to it, again, we're trying to find those best fit values for the parameters that we're using to define the model. So again, what type of parameters are being used to predict our given outcome? And so what we see is with a model, the nice thing about it is that, again, it's a representation of something else. It's not always going to be, usually it's derived from some sort of specific data, but then gets applied to other, used as a kind of a predictive model. And the nice thing here is it's usually less expensive and more accessible, and a lot easier to manipulate than having to deal with a very large set of patients. And again, it's just a mathematical model. It's just using either one equation or set of equations to try to either describe, represent, or at least try to approximate some sort of biological state or process, chemical, physical process, anything like that. One really good example we did for a journal club last year was they were trying, one study was trying to determine what sort of presenting signs and symptoms were more likely to be indicative of a pulmonary embolism. And if you could figure that out, you could decide, more likely who needs a CT scan, who needs to who needs to receive thrombolytic therapy, things like that. And so by using a model, you can try to apply that to other situations where you're dealing with people who need to try to rule out or rule in things like a PE. So anyway, what we'll find is that using models can also help us to design better experiments and try to comprehend the results that we get from some experiments. And we'll see that by fitting the models to data, we can then simulate data back from the model. So kind of you start with a set of data, develop your model off of that, and then now you can try to basically estimate or at least try to simulate data that you would get if you applied that back to a larger population. So again, we're fitting model to the data initially, and so usually we're using a regression that will fit a model. We'll come up with an equation for a line. We're doing one of these kind of simple linear regressions, and so we adjust the values of the parameters in the model and try to use that to make predictions of the model as close as possible to the actual data. So again, we're trying to find the best fit line, and you see that basically regression does not fit the data to the model, but rather we're trying to fit a model that is going to fit to the data. So the way you can kind of think about it is that the data are like your feet, and we're going to be conforming shoes around those feet rather than the other way around. So again, the data has to come first in these situations, and then we design a model that's going to fit that. So that way you don't try to cram in size 13 feet into a size 8 shoe. Rather, you start with those size 13 feet and say, okay, well, this is the type of shoe I'm going to need to cover that. Okay, so moving on, now we're talking about comparing models to one versus another. So we see is that comparing models can be one of the major parts of statistics that we'll deal with. And so what we see is that with models, with more parameters, they always tend to fit the data better, but they may not actually reflect what's going on with the population. And we saw that back in that previous example when you were dealing with the insulin sensitivity question. You saw that the R squared value was something like 59%. So only 59% of the variability between those two variables could be explained with that type of model, right? And so what we can look at is to use multiple inputs, right? So multiple different parameters to try to better fit that data or the line to that data. And so again, we can use kind of different comparisons of different parameters to try to see which gives us the best line. And so useful comparison has to take into account that number of parameters fit by each model. And so what you find is that a model that has too few parameters typically does not fit the data super well. It's not going to be super tight of a fit there. But if you have too many parameters, you may fit the sample data very well, but you're going to find that the confidence intervals tend to be so wide that that range you're really saying that, hey, the actual population line fits between these two marks. It's so wide at that point that it's not going to be super clinically useful for us. So again, when we're looking at different models, basically we're trying to say that, well, the initial null hypothesis, and you can see it here in this case, is that on the left one, the null hypothesis is that there's no variability that's explained in insulin sensitivity by this percentage of these fatty acids. So again, a straight line, a straight horizontal line, or a line of 0 with a slope of 0 would again be the null hypothesis. Versus what we can compare this to our model where we have our linear regression. We can see that, okay, well, we think that this is not just due to random variation. We think this is actually truly refining that that percentage of the fatty acid composition is going to have an influence on insulin sensitivity, right? And so when we're looking at the R squared value, we mentioned that that linear model, when we're looking at this, tends to fit that data much better than if we simply drew a straight line. So you can graphically you can kind of see that. And so what we see is that by finding a line that has less variability of the points around that that null hypothesis horizontal line, you get something that is going to fit much better. And so we can start to say, hey, this is less likely to be due just to random chance, and is truly one can kind of start to predict the other. Okay, so when we're looking at that R squared value, so again, looking at our null hypothesis, meaning that that horizontal line or the slope is 0, meaning that there is no real, you cannot predict y from x. Basically, we're saying that if that's true, then we can see that the percentage of variation that is just due to random chance is 100%, right? Because again, one has no relation to the other, so all that variation there is just due to random chance. And so we'd see 100% of variation there. Due to that. What you're trying to do is when you come up with the best fit line, you're comparing it to that null hypothesis, and so we can see our regression line. And so what we see is that now this percent of variation drops down pretty significantly because there's a lot less variation around from the data points we have around that line itself. And so one of the things they look at is the sum of squares. As long as this number is getting smaller, it means you're having a bigger, the more tightly that the line is fitting to the data. There's less variation around those points there. But anyway, so you're looking at the improvement, and so this is where we got that 59.3, and this is actually our R squared value. So what we're saying is that we're predicting that basically 59.3% of that variation can be explained by changes in our x value when we're trying to predict where y is basically going to be. So, linear regression is really the simplest way that we can do a regression, but it's not super useful clinically because, again, patients are going to have a lot of factors that are going to influence many aspects of their health. You're looking at socioeconomic status, looking at their previous, hospitalizations or comorbidities, or lots of things. And so you want to be able to factor a lot of these in to try to get a better picture of what's going on and how we can predict certain features or certain things. And so this is where we're going to talk about multiple, logistic, and then proportional hazards regressions. So first thing we're talking about is this multivariable regression, or multivariate is sometimes how you'll see it described. And so what we can see is in the laboratory experiments, we control all the variables ourselves. And so as we change one variable, we can measure another and then analyze that data with our standard statistics tests. We can do t-tests, we can do chi-square tests and things like that to determine if there's any statistically significant differences. And so again, in some kind of experiments, you have to analyze how one variable is going to be influenced by several different types of variables. And so this is how we're going to be getting our multivariable regression, is where that term comes from. So, like I said, in some kinds of experiments, and usually in a lot of observational studies, and again, observational means that we're not really having any sort of intervention. We're just simply observing things that are happening. We're categorizing patients or something based on characteristics, right? And so we're not having any direct influence here, but we can see that the outcome that we're measuring in those patients may be affected by multiple other variables. And so we can use these multiple variable methods. They're very powerful, very versatile, and we use them very, very frequently. So when you hear kind of a multivariate regression analysis, these are used pretty commonly in the medical literature. And so here we're just going to talk about the basics, so that way when you see one pop up in the literature, we can kind of you'll have a better understanding of what they're actually doing. And so again, one thing we can do is that we can assess the impact of one variable while adjusting for others. So for instance, if we want to adjust for the effect of smoking on heart disease in patients who are overweight, you can do things like that. We can create equations for making very useful predictions about things like, does someone need a CT scan to rule out PE, or are they at a higher likelihood to die based on certain things? And then it helps us to understand basically how multiple variables will impact on a specific outcome. So some things you'll see with the different types of multiple regression, there's lots of different methods for this. And again, as long as we're using multiple variables here, we can always consider these to be multiple. And so the variables we're looking at all predict a specific outcome. And again, that dependent variable, because again, in this case, the kind of output variable of this dependent variable is dependent on whatever we're setting as our x, or inputs essentially. So y is going to be our dependent variable, and then from one or more predictors, we're going to call this the independent variables, and this is going to be on our x-axis. Again, multivariate is a term that is used pretty inconsistently, and so sometimes it can be referring to the methods that simultaneously compare several outcomes at once, which is the correct means for it. But sometimes people refer to the methods used when there is just one outcome and several independent variables. And so really this is considered to be multivariable. I'll probably be the first one to own up to making mistakes on that as well, and because people routinely mix these up. So again, you have multiple, basically one outcome and multiple independent variables. This is considered multivariable, but when you're using methods to simultaneously compare several outcomes, this is called a multivariate. So again, clinically, it's probably not going to come up, and no one's really going to call you out on it. And if they are, they're probably a bigger statistics nerd than you ever really want to associate with in the first place. So multiple linear regression, we're going to see that we can find the linear equation that best predicts y from multiple independent variables. And so one of the things that we can, one example of this was, does lead, and again it's the lead, the metal, account for decreased kidney function with age? So this is a study back in '92. And basically what they were trying to do is investigate this relationship between lead exposure and then kidney function. Lead is something we know to be nephrotoxic, and so we know that also kidney function decreases with age as well. So this is one of those things where now we have multiple variables that are affecting our outcome, right, which is kidney function. And so we'll often will find that most people accumulate small amounts of lead as they get older. And so this is something where we can look at multiple independent variables and try to determine how this will all have an effect on our dependent variable, which is going to be our kidney function here. So the specific question we're asking is whether accumulation of lead could explain some of this decrease in kidney function with aging, or if it's specifically just due to age or maybe some other variable that they're not looking at. So here they were looking at 965 men. They also studied some women, but we're only going to look at the data for the guys in this situation. And they measured the serum lead level, and they also measured their creatinine clearance. And so what they found was that subjects with more lead tended to have a lower creatinine clearance. And again, this is not a useful finding, as we will see that lead increases with age and creatinine clearance anyway. So it wasn't going to be super useful right off the bat there. But we want to find out if these differences in age would confound any investigation between that creatinine clearance and lead concentration. So you need to be able to control for some of these independent variables to determine if they're going to have any effect on our dependent variable. So in this case, we call these confounders. They're going to be confounding our data and prevent us from showing some sort of outcome that's really there. So again, in the statistical sense, it's an extraneous variable that correlates either positively or negatively with both the dependent variable and the independent variable, right? So we can call age being a confounder, and we need to take this into account when we're doing our analyses, and this is what we'll see as we go forward. So again, here to adjust for the co-founder, the investigators use multiple regression analysis to adjust for age and then other factors. And basically what you're doing is you're taking out the influence of things like age or other factors in order to just look specifically at lead levels and the creatinine clearance, right? And so we can do that using some pretty sophisticated statistical methods. And again, our X variable is going to be the log of lead concentration, mainly because this is kind of a multiplicative value. So again, they're just looking at the log of that. It tends to be a little bit easier to look at concentrations over a large scale. And then we're going to see that this is our independent variable, and then our Y variable, which is going to be dependent, is creatinine clearance. And so what we find is we're generating a model based off this data of roughly 1,000 men, and we want to predict its value from a baseline value, right, plus the effects of these 5 independent variables, each multiplied by a specific parameter. So and then we'll go into more detail on this in a second and see what this looks like. So some of the things that we're looking at is basically looking at the log of the serum lead concentration. They're looking at the age and what effect this had, body mass. They would also look at the log of this GGT. GGT just being a marker for possible kidney injury, as we'll see in some patients. And then they also look at diuretics, and this was to determine if diuretics were having any direct nephrotoxic effects here, or at least having any effects on the kidney function. So again, we'll see that you can use different variables, and they can all have different units for sure. And so we can find that here we're looking at the log of the serum lead level. We can find that age is obviously done in years, and so it really doesn't matter what type of variables you're looking at. They can all be taken into account when using these kind of multivariable analyses. So the goal here are multiple regressions trying to fit the model to the data that we have from these 963 men to find the values for these coefficients that tend to make the model come as close as possible to predicting the actual data. And so again, this is a best fit value for each parameter along with the creatinine, along with the confidence interval, I should say. They're going to go along with those. And you'll see that one p-value is going to be reported for each independent variable to determine whether or not either of those has any specific ability to predict creatinine clearance. And what we'll see is that our null hypothesis is that the parameters provide no information to the model, so that the b parameter value has a parameter that equals 0. So essentially, they're finding is that the horizontal line is going to be there. We'll have a line with a slope of 0, and none of the variables that we're looking at are going to be able to explain our dependent variable, which is creatinine clearance in this situation. So, we'll look at interpreting these coefficients, and what you see is that these multiple linear regression models do not distinguish between the x variables that you really care about and the x variables that you are adjusting for, these covariates. So again, our main thing we're looking at is lead levels and creatinine clearance. Everything else is what we call our covariates. And so when you run this through the statistical software, it's just going to pop out a bunch of p-values at you, along with other information about these kind of best fit lines. And so the big thing here is you have to make a distinction when interpreting these results. And so again, the investigator's goal is trying to answer that after you adjust for the effects of the other variables, is there still a substantial linear relationship between the logarithm of the lead concentration and creatinine clearance? So basically you can control for these other variables like the GGT and diuretic use and all of that to try to take out those confounding factors and determine specifically, is there a relationship here between log of lead concentration and being able to predict creatinine clearance. So what they found in these results was that with the best fit line for lead, they found the slope was negative 9.5 mLs per minute. And so what they found was when you adjusted for all the other variables, they found that one increase in the unit of lead is associated with a decrease in creatinine clearance of about 9.5 mLs per minute. They saw a 95% confidence interval between negative 13.9 and 5.1. Notice this does not include 0, and so that means that this would be statistically significant. So I don't even have to look at the p-value to know that. And so essentially what they're finding is that a 10-fold increase in your lead concentration would reduce your renal function roughly about 10%. Again, a confidence interval would range anywhere between, say, 1 to 20%. So here's a graph of the best fit line for the data, and this is again accounting for all the other variables that we talked about previously. Essentially what you see is that the y-axis here is going to be our dependent variable, which is going to be our change in creatinine clearance. And again, notice this line is negative. It's going to be going down because, again, we find that there is an inverse relationship here, whereas lead levels increase, you're going to find a decrease in creatinine clearance. And so essentially, notice how the 95% confidence intervals get larger and larger as you get higher in the concentration. And that's because we're dealing with logarithms here, where, again, one increase in unit of lead concentration indicates, a 10 increase in-fold in lead levels. So basically, as you get, larger and larger, 10-fold increases in lead, that's obviously going to have a much bigger effect on creatinine clearance. So again, here's the best fit line. Here's our 95% confidence interval that we could apply that back to the larger population here. And in this case, because we're only looking at the male data, we can only apply this back to male patients, because obviously we didn't account for the female patients in this case. So as far as statistical significance go, we saw the confidence interval, this beta 1, or this, our lead concentration runs from the negative number, does not include 0. So you can be 95% sure that by increasing lead concentration is going to be associated with that drop in creatinine clearance. We can presume the p-value to be less than 0.05, even if the authors don't quantify in this case, because we know the confidence interval does not include 0 in this instance. So we have the full model, and again, we're looking at all these independent variables. We're going to find that the r-squared value actually ended up equaling 0.27, which means that with that model and all the different variables we were looking at, only 27% of that variability in creatinine clearance could be explained by the model. That means that the other 73% that was there is going to be considered to be due just to, it's going to be considered random. Variability in those points around the line. And so again, there's no good way to have a best fit line. Again, here we're going to have too many independent variables that we're looking at to really give us a good clear line, just because there's so many different factors that are there. And then again, we're just seeing there's a lot of variability there. And so even though the r-squares we're going to find is going to be a p-value less than 0.05, meaning it's going to be statistically significant, it doesn't mean that you have a model that really can explain a ton of variability. And here you have a graph where each one of these points is going to be one of the different men that were involved in the study. And you can see the R-square value 0.27. Basically, the line they have here, this best fit line, you can imagine several other lines that were kind of going in very similar directions and probably have similar variability around. My lines are not very good, but you can see how multiple lines will probably have the same variability around those points as the actual line that's documented there. So again, not a great model because it doesn't explain a whole ton of things, but it's nice because you can control for lots of different factors and try to look at one independent variable to see what effect that has on your outcome. So again, correlation does not imply causation. So again, with when we're looking at this, when you have an observational study like this, where we're not really intervening, like we're not actually giving people lead and then determining what changes they have in their kidney function, it doesn't really give you a lot of ability to determine cause and effect. Really, you can say that there is a correlation here. You can say that this can predict things, but you can't say necessarily that this increase in lead absolutely causes decrease in creatinine clearance. So that's one of the problems with using some of these observational studies versus using more of a basically, kind of an experimental study where we actually did a true intervention. And we'll see some examples of that when we look at the actual literature here. But the best way to do this actual kind of study would be to start off with 1,000 people and start at time point 0 and then monitor their lead levels and see what changes. So usually you see prospective experimental studies tend to have a lot more kind of validity to them and a lot more cause and effect can really be determined from those rather than just simply looking at a group of people, especially retrospectively, and determining what kind of associations are there. But with this kind of model, you can see how it may help you to design future experiments where you may look at some of these specific things like lead levels or the GGT or whatever happens to be. So again, these are very good because these kind of studies are pretty easy to do as compared to like a prospective experimental study. But it is not going to have as near the kind of you can't really take as many facts away from it as you could if you did like a prospective study. So anyway, another thing we can do is called a logistic regression, and this is going to be used when there are two possible outcomes. And so an example here is a study done in 2008 where they're trying to predict the prevalence of obesity in Iranian women. And so they considered our outcome to be binary, because again, they're either considered to be obese or not based on whatever metrics they're looking at, like BMI or something like that. And so what they did was they created a model to try to predict that prevalence of obesity as a function of various demographic variables for these women. So they were looking at 3 different independent variables, and again, these are the things that we are measuring about these women to see what type of effect they're going to have on the outcome or dependent variable. And they were looking at age and number of years of education, which are continuous variables. We're looking at smoking status, marital status, which are considered binary because single, married, smoking, non-smoking, and some place of residence. That could be something like rural, city, things like that. They tend to be, you can make those binary. And they also looked at their economic index, and they used 4 different categories which they were assigning binary variables to those as well. They had roughly 14,000 women they were looking at. That was their N value. And then they were using logarithms. What you can find is with odds ratios, they tend to be asymmetrical, but by using the log of the odds ratio, that tends to make it more symmetrical. Again, not super important point for us to take away, but that's the reason why they did that. And so they made an odds ratio for each independent variable to see what effect that would have on our dependent variable. And so the example we have has 8 independent variables. So the model has basically 8 different odds ratios that end up getting reported. And so each odds ratio basically answers the question that if one particular x value were increased by 1, meaning you keep the others the same, how much would the logarithm of the odds ratio be expected to increase? So basically what it comes down to is that by looking at these odds ratios, we can find kind of what type of impact this is going to have on our dependent variable, or in this case obesity. So an odds ratio that is near 1, and again, because we're looking at ratios of odds rather than looking at, say, like a relative risk or something like that, or like a relative risk reduction, we can see that our cutoff point for significance is going to be 1 in this case. So again, odds ratio of 1 or very near to 1 would mean that the independent variable had really little impact on the outcome. It really didn't matter what that variable was in causing a person to be obese or not. If you were to see an odds ratio much higher than 1, then that would increase the likelihood of that independent variable, or an increase in that independent variable is associated with an increased likelihood of the outcome occurring. So if someone who had if a variable had an odds ratio of 2 or 3, that would mean that your odds of being obese, if you had that particular variable, is 2 or 3 times higher. Odds ratios less than 1, though, an increase in that would end up seeing a decreased likelihood of our event occurring, or in this case, obesity. So again, if our model is correct, then there would be an ideal population value for each of these odds ratios, and you could use it pretty predictively to go back and say, hey, for these Iranian women, if you are educated, if you have this age, and you are smoking, and blah, 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 you could pretty well predict whether or not that person would be obese, essentially. So what they did when they're looking at this, we can see several odds ratios that get reported here along with their confidence interval. And again, we're going to look at to see whether or not these are going to be significant or not. And so we see, okay, look at that first odds ratio, urban, right? So are they living in an urban center or not? So urban, having an odds ratio of 2.13 that range between 1.9 to 2.369. So because this is higher than 1 and our confidence interval does not contain 1, we would see that being in an urban setting would increase your odds of being obese. Looking at age, we see the odds ratio came out to be 1.2, or 1.02, I should say. And you can see the range here, even though it's pretty tight, it's very, very close to 1. So actually, age had a very small impact on whether or not someone was obese, even though it was considered to be significant, because again, this does not include 1 still above it. Education also seemed to have a kind of a protective effect. We actually saw that this decreased the odds of someone being obese, but again, a very, very small impact here, right? So education tended not to have much of an impact here, even though again, this was significant. It does not include 1, it's below that. Smoking tended to be also protective, so this saw a decrease in the the odds ratios of someone being obese. And again, another significant. Notice confidence intervals are wide here. Being married increased that likelihood. Lower middle class or upper middle class also tended to increase the odds ratios of someone being obese, and then being higher class, kind of higher socioeconomic status tended to increase that as well. So here we can see that really the thing that had the biggest impact would be the urban setting. What type of environment they're living in tend to have the highest impact on whether or not they were, the odds that they were going to be obese or not. So again, that logistic regression computes an odds ratio for each independent variable along with that confidence interval. And so, and again, when a subject lives in the city, that corresponding odds ratio is 2.13. So a subject who lives in a city has more than twice the odds of being obese as someone who doesn't. Okay. You're going to find that the other independent variables are going to be, that's assuming that all the other independent variables are identical. Or essentially, when you control for all those other ones, what is the impact of this one independent variable? And again, because the confidence interval for that one range between 1.9 to 2.4 does not include 1, you would conclude that that p-value would be less than 0.05. So again, the chances of that, you finding that kind of odds ratio just due to chance alone is very low. So you can reject that null hypothesis that living in an urban center or not had any impact on obesity. Okay, so starting off with a little Q&A. Do the x and y values have to have the same units to perform a linear regression? Can linear regression work when all x values are the same or when all y values are the same? And will the regression line be the same if you exchange x and y? We find that for x and y values, they don't have to have the same units. They certainly can. But again, in our example previously, we saw the x and y, insulin sensitivity versus percentage of fatty acids, was certainly very different units there. So it doesn't really matter. And can linear regression work when all x or y values are the same? No, because again, if there's no variability in y or x, then you can't really use the other to predict one. You can't really predict y from x if all the values are going to be the same. So again, there's really nothing to predict in that case. Will the regression line be the same if you exchange x and y? Again, we're using correlations, not really making any predictions. You're just looking for a relationship. You can do that. But with linear regression models, we're trying to predict y from x. So if I swap the definitions of x and y, then that regression line will be different unless the data points happen to line up perfectly so that every point would end up being on the same line, but oftentimes that's not the case. So you cannot switch those out because, again, you're trying to predict one from the other. You always have to decide which variable is the outcome dependent and the predictors independent at the time of data collection. Does it make sense to compare the value of one best fit parameter with another? And do all the independent variables have to be expressed in the same units? So for the first question here, you don't always have to decide which variable would be your outcome versus your predictor. In a lot of cases, it may not be very distinct at the time of data collection, and so sometimes the decision gets made during analysis. It should be done with caution because you don't want to keep looking at different variables and kind of putting something together, kind of jamming puzzle pieces together until you kind of fit something to the data. But and it needs to make sense when you're trying to use one to predict something else, right? You need to make some kind of biological or physical sense. Does it make sense to compare the value of one best fit parameter with another? No, you actually find that the units of each parameter tend to be different, so they can't really be directly compared. There's some advanced methods you can do to do that, but we're not going to be covering that in this course. And then do all independent variables have to be expressed in the same units? No, usually you're going to find that independent variables are going to be in different units, just like we saw with that lead example. So again, if you have any questions, feel free to email me, and otherwise we'll go on to the next section.